All right. Welcome to Friday at DebConf. I'd like to introduce T K Sourab, talking about what's due in eBPF.
Thank you. Good morning. I got a lot of slides to go through, but I hope everybody's doing good. Awesome conference dinner. So bear with me. I will talk about eBPF today. I have tried to make it a gentle introduction and how you could start using it today. Right. So about me, I am currently part of the compute team, and I used to work at Red Hat, and I used to organize Linux meetup groups, and that's me. We went for the day trip. So today's agenda is introduction, and then we'll talk about eBPF, how does it work, and how to use it. And we'll try to, if you have time, we'll try to cover some use cases. Right. So I hope everybody has heard or used TCP dump. So this is a tool that essentially also used in Wireshark. It does packet filtering. It's used for network debugging, and this is how it looks like. Internally, if you try to, take a look at the assembly code instructions, it is a special purpose virtual machine that were created. So these are the instructions, and it's in kernel. That means the packet processing happens inside the kernel with its own custom instruction set that we just saw. Does packet filtering, aggregation, and returns to user space. We all know this. So why was BPF or TCP dump created? Because we wanted to do packet filtering in kernel so that we don't have to travel up the stack. So the user space, if the packets travel up the user space, it requires a context switch. So instead of that, if we want to do packet filtering, we can do it in kernel and only care about the packets that we want to filter up the stack. So this is how the original architecture looks like. It did a copy, and it was able to filter them and then send it up to the user space. Right. So then there is something called eBPF now. Previously it was called BPF. Now it's eBPF, which means extended BSD packet filter or Berkeley packet filter. So it was created because there was a lot of use cases that came up during while SDN was coming up. So people needed a way to able to parse packets early on, and that's why eBPF came across. So the difference is essentially they moved to 64-bit registers, and they increased the number of registers count from 2 to 10, and JIT support added, and then finally the BPF system call got added. Right. So whenever we refer to BPF now, it's eBPF. The older eBPF is called CBPF, classic BPF. But internally, even if you write TCP dump or classic BPF code, it gets translated to eBPF as of today. So because of this, there came a huge set of use cases which are like quite endless. I think people working in different area, you might have heard about in networking, Cilium and XTP, or network security, these kind of toolings, as well as for tracing observability. These are another use cases, as well as SecComp is one of the use cases. LSM BPF is also there. So a lot of use cases came up. So how does eBPF work? Essentially, I made this diagram some time back to be able to understand how it works. So in a gist, I'll explain all of this throughout, but you essentially have a user program that gets compiled by the BPF LLVM backend that the LLVM has to a bytecode, and then the system call is used to load that program into the kernel. And inside the kernel, there is a eBPF verifier, which verifies the program to make sure it is safe. And then once it is verified. It is able to attach into multiple hooks that are available in the kernel, which is, depends on the use cases. There are tracing hooks, socket filter hooks, XTP, TC, and much more, like a lot more. And the way they talk to the user space, so we want the communication to happen from the user space. Exchange of information should happen. So the way it happens is via the eBPF map on the right side for you. And then we can use something called an in-kernel helper function. So I'll talk about this in more detail. Right, so this is essentially the system call, and we have the first parameter, which lets you create the maps or a program, BPF program, or load the program, which is the last one, the BPF program load. Can I do mouse cursor? Yeah, and you can specify the map types and the size. So this, at a high level, that's how it looks like. Let's talk about maps. So the first command that you see, BPF map create. So the maps are data structures that lets you talk from the user space to the kernel side and vice versa. So they return a file descriptor to you, and you can access that file descriptor up. But the way to access those maps is via in-kernel helper functions, which is BPF map, lookup, update element, these kind of kernel functions. So there are a lot of types that are available, map types. We have hash maps, arrays, program arrays, which is if you can attach one program back to back. And there is perf event array, which lets you, it's similar to perf buffers, lets you, it's the same thing, so it lets you exchange data. But right now there is a new type, which is called a ring buffer, so that you can use now to exchange data. So there was an issue with ordering of the data that came into the perf event array. So with ring buffer, that issue has been solved, so it's a newer type. Recently, there's a fairly new heap sort of structure called BPF Arena, which I won't divulge, but you could look it up. And Bloom filters, per CPU array, lot of stuff, lot of map types are there. So how you create map is with this call. I don't think you have to use it, but I'm trying to just get through how it works internally. Most probably you won't use most of this unless you are developing core BPF programs. So you have your map type array. So for example, we talked about the types. So the type get fed here, size of the key and value and things like that. So on the left side, that was the old BPF map structure. On the right side, you have the newer structure. So I'll explain why there is a change. But right now you have this on the right side. You have that's the new type of maps. Right. So we talked about how to access those maps. That's the lookup element and update element, the one that's marked in red. Right. So we talked about these are in-kernel helper functions. So in-kernel helper functions are essentially functions that lets you access kernel structures. So these are a safety mechanism, and these are quite stable right now. The kernel is not letting us, or in principle, is not accepting new helper functions. But these helper function essentially lets you access maps and other things which are harder to do if you were to do it, or you won't be able to do because it's not allowed. So the other mechanism is kfuncs, kernel functions, which lets you, but they are not stable. Whereas the helper function is defined and quite stable, well tested. Yeah. So you have various types that I talked about. Like we have various use cases. So that's where the program types come into the picture. So they have hooks. That means there are points inside the kernel that lets you, if a program is attached, the code will move to that BPF program and run the instructions that we have wrote for BPF program in a virtual machine, eBPF virtual machine. And then comes back once it's done. So that's the hooks concept. And there are BPF is able to do K-probes, use the K-probes infrastructure as well. So if you have K-probes points, you can also use those. Recently, there is something called F entry or function entry, function exit. So on a function entry, you can attach programs, or on a function exit. The one difference is the caret probe, which is the return probe. You are not able to see, I think, the input, the parameters, but with the function entry and exits, you can see both of them, the return statement and the input statement, at the same time. Right. So these are the program types. I talked about K-probes, and you have networking related hooks. Right. So how you load the program is similar to what we do the maps as well, but with the change in BPF load program, and it essentially will eventually goes to the BPF system call. But this is how it looks like. Yeah. So anything you're trying to run in a kernel, you are not confident, right? It's not going to be safe. Like kernel modules have its risks. So is it running in a VM makes it safe? Not really, but you have something of a layer in between called a verifier, which makes sure your program is safe, memory safe, and ensures that the program doesn't has a definite termination. It doesn't, loop around and goes, it has to terminate at some point. So the verifier ensures that. Excuse me. Yeah. So then we have the steps of the verifier. These are the two steps that it does. It does a lot more, but in a gist, it tries to follow the path of the code, follow the instructions, and it does something called bounded loops, which means even if you have done a for loop inside your BPF program, the verifier will go through each of these loops. It will unroll, but the unrolling is a different concept, but this one I'm trying to use the words, but it tries to go through each of the loop process and tries to see whether it does have definite termination. And the other thing it does is dead code elimination. If there are some code that is not reaching, it will just remove those. And so it's a very strict verifier, so you have to make sure your program is terminating and good. Right. So the resource limits on BPF is controlled by R limits. Some time back, you had to have the CAPSYS resource capability. Right now, they have added C groups. So now in 5.11, which is the kernel version, you can use C groups. And you also have unhinged access with the no BPF, memory access with the no BPF in 6.3. Right. So essentially, everything that we talked about will look like that. So the program gets loaded by the system call into a verifier. The verifier verifies the program, and the program gets attached into the hooks. And then the way to talk with the user space is via eBPF maps. Right. So how do we use it today? Right. So this is you need to at least have, the best way to do is, you get the latest kernel, but the system call got added in 3.18, which is a while back, and slowly more features are coming up, and there is effort for backporting as well. So these are the flags or configs that you require. Right. So how do we use it today is, this was the old one, the classic BPF. The TCP dump internally, this is how it works. You have some instructions. It's not clearly writable. With extended BPF, when it came up, this was how the program looks like, which is again not readable. And with support of LLVM, we are able to get to some stage. We are able to write a subset of C, and there's something called BCC, which is BPF compiler collection, which somewhat makes it easier, or actually makes it a lot easier to write in Python the program the eBPF programs, and it lets you do quite a lot of things. So a BPF program in BCC will look something like this. You have to embed your program, BPF program, which is what runs in your kernel. In the red, you can see that is a C program, and then on the bottom, you can see the Python program, which is the user space. And in this particular program, it's trying to send the data back up. So it's trying to do, first it's trying to attach a unit probe, so it is a user probe, and it's trying to read those events from the B variable and print it out. That's fairly simple. The complex thing is the C part, but that's also, you can see the events.perf submit. That's how it's trying to put the data onto the maps. And the same thing in the bottom, you can see it's trying to get it back. Right. So with BCC, this many tools exist now, or more, or you could write your own. That lets you, this at least this is for the tracing use cases. So you could trace pretty much most of the subsystems that we have today, including the user space. So there are Python programs as well, and it's fairly easy to run. You just need to, they are packaged in almost all distributions very well. So you could start using them up today. Right. So there's something called BPF trace, which is an even easier way for you to start using it. This is similar to your dtrace if you're familiar, and it lets you, it internally uses BCC. So how we go about doing it is you have two options. You have one-liners. You can start tracing your kernel or system calls in just one single line on the left side. And on the right side, you wanted to do a little bit more, print statements and things like that. You could do as a script manner or a one-liner, either up to you. Right. So if you want to write eBPF program, explain. So you explained about BCC. You can start using that. But the problem is, with BCC, you have to compile for each and every kernel. It requires your kernel headers, and this results in large binaries. Right, so that's an issue, right? You might not have, if it's for a single system and you're trying to trace something, it works. BCC is perfectly fine for the most use cases. But if you want to deploy BPF programs in large machines, you don't want to worry about it whether the kernel headers are present or not. You just want to deploy it across, and it should work. The BCC will not. It's not the best. The BPF core, which is compile once and run everywhere, that's a newer component that came up. So how it works is it requires two things, which one is BTF, which is not BTS, but BTF, which is BPF type format, which lets you, get information about the kernel type definitions that are there, and how you enable is with the config option that's present. And once you get that information out, the Clang compiler also has this ability. So for example, if I wrote one program for my systems, it might not work for yours in case of BCC, but in case of core, you have something called field offset relocation. That means in my kernel, the struct will exist in some line of code, but in the kernel that you might be running, it would be in a totally different space, so it might not work. But with the Clang field offset relocation information, it's sort of a way to for the program to figure out that, hey, there exists a PID struct that exists in the structure. So it will try to resolve that and find that particular information that the BPF program is trying to access, and just relocate the program or resolve those issues. So with libbpf, it takes all those information, BTF, field offset relocation, and it tries to load the program. It tries to first read the program and tries to load the program, so it will run for all kernel. And right now, the BCC tools that you saw a while back in a big diagram here, so these are being actually ported to libbpf. You can see in the bottom. Right, so to get started, you need Clang 10, and you have something called libbpf bootstrap, which simplifies a lot of things that you want to do. It automates a lot of setup work. You don't have to, so as comparison to your kernel development, you have to have a lot of setup work that you have to do, but with BPF and libbpf bootstrap, it's fairly simple. Right, so there's something called BPF tool, which is a debugging tool, you could say, or analyzing tool. It lets you see the programs that are loaded and look at the maps. That's possible because of the BPF information, BPF type format. And it lets you also create your own VM-linus header file with the kernel type definition. Essentially, you might not need the kernel headers. Right, so, and it also exposes information that might not be available with the kernel headers. Right, so we talked about, the faces. So these are like the 4 faces that are essentially there. We have the open, which is where the program, BPF program, is read and understood that, hey, these things exist, but it's not created. So the ones that end with the underscore under open, those calls. And then you have the load, which is where the BPF program gets loaded. Verifications happen here, and maps are created in the kernel. It can happen at the same time. They don't have a race condition there. And finally, the attach program is where, attach phase is where your program gets attached into the hook points and the program starts doing something, right? And that's where, pretty much your program will run for a long time until you do a destroy or tear down. That means essentially remove the program. These are essentially the 4 life cycle or phases that you call right. So the libraries that are present, you could do, you have a lot of libraries that are available, but like libbpf is the core, but the first 2, I think the last one as well, I'm not sure, but the first 2 are a pure Go and Rust implementation. These do not really use libbpf, but they try to be as compatible as possible. They try to use the core infrastructure, but if you want to do something in Go or Rust, that's where you go. There are actually multiple libraries companies have built or people have built, and somebody's trying to do it in Java as well, so you could write Java code as well. Right, so I'll just talk about XTP for some time. So XTP is Express Data Path. This is a networking use case. This particular hook runs very early in the networking stack. This is before your socket buffer gets allocated, and it's just after the packet reaches the driver. So this enables you to have extremely fast networking capability, and like most of the use cases, you might have to travel up the stack. But in this case, you don't have to. Like within the device driver itself or L2 layer itself, the packet can be processed, and it doesn't take up CPU cycles. Yeah. So what's good about this is it doesn't bypass the networking stack. Like you can access pretty much all the infrastructure that is there, the data structures as well, and it doesn't take up the whole NIC compared to DPDK, and it's part of the kernel tree, so it's well maintained. Right, so these are the resources that I talked about. We have a lot of resources that are available. This is just some of the links, but the first link should be exhaustive, the eBPF.io, which is a foundation link, and you could access pretty much all resources there. That's a one shop for all, right? Or you could look at kernel documentation or whatever, libbpf, XTP tutorials, and reference guide for more information, right? But eBPF.io should be more than enough. Yep. Thank you so much. That's the talk. If you have any questions.
All right, do we have questions?
Someone who doesn't know much about eBPF applications, I mean usage in the real world, and looking at all of this, I have a maybe stupid question. Is it maybe growing into something which doesn't belong to the kernel? Something like too big? I don't know. Like these things you showed, additional things and other additional things for these additional things. So yeah, I'm probably wrong. I'm just curious. What do you think?
Yeah, I think it's all part of the kernel. So, I mean, it uses a lot of, for example, tracing use cases. It exists, right? K-probes exist already. So it just uses those existing infrastructure. I mean, it seems very big, but it's just reusing everything. BPF already existed. The only change is you added some more registers to it, and which lets it be more programmable. There are features that being added, and you could add the option, kconfig and remove if you don't want a lot of features. Right? People do that. Not just for BPF, but everything else. Whatever they don't want, they can remove it for embedded systems specifically. So that's there. So kernel is big. People just use what they want. Thank you.
Do we have any other questions?
We can hang back and talk. Okay.
We have been using BPF in the TC, traffic control.
Yeah.
But can you please compare which usage should be better as XDP and traffic control? Which is better, or which is more suitable for which usage?
Right. So TC is more. TC is traffic control. Yeah. Is more. You have ability to control the traffic, both are good, but it depends on your use case. So some people do use TC and some people use XTP. So XTP is much earlier, and there's something called AF XTP as well, which lets you do it. Manage it from the takes the packet from L2 and takes it up the user space. So similar to how DPDK does it. But I'm not sure the comparison. It depends on the use case exactly. Not sure how to answer that, but it depends on use case.
I want to hear your real-life case. So, for instance, you made a critical issue, and it might take a few days to solve it, but you did within maybe for about 1 day or less than by using eBPF.
Okay, so I can, tracing is there. I've hidden some slides, but how do I show? So I do have some here that talks about the real life cases where I was doing some DDoS test scenarios. And I did face, with this thing, some issues where I was not able to find the performance that's expected. So I tried to use it for my cases, but it was not, we're not able to get it. So it's something that comes in debugging. So I can remember one case I think I read up, which might be more relevant. is right. There was one company that was trying to. They were facing issues in spikes, so they with the writes. So the writes were happening to the VFS driver, which is the virtual file system driver. So the writes were happening. They were buffered, but they were not happening as fast, right? So they were not flushed as fast. So with that, they were able to use BPF to find the tail calls, right? So why are they taking that much time? They were able to build their own tooling. They were able to write their own program instead of relying on kprobes, dtrace, or whatever tools were available, system tap or whatever it was available. But they were able to write a program. So, like, if the existing tool doesn't exist, you can write your own stuff. So they were able to write, and they were able to figure out that, hey, this was where the tail call latency is quite high. That's where the buffering was happening with the data that was trying to be queued up. And they found the issue, which was, it was an ext4 issue. So if they changed the file system to XFS, that was a solution. But the debugging step was to find that tail call, which was happening that slow. And XFS has some kernel features or features that is fast commit or something like that, which lets them commit flush the data quite fast, so that latency they were able to minimize. So these are the cases. If you do not have the tools, you can write the tools that you want with BCC and libbpf if you have that expertise. For BCC, it's fairly simple. It's written in Python, and it's fairly easy to do.
Okay, thank you.
Do we have any other questions? All right. Let's have another
Round of
round of
applause.
applause for our presenter.